I welcome you all to this 4-week MOOC course on analog electronic circuits. Week 1, Lecture 3. It is electrical equivalent circuit of BJT and FET. So we can see in this front diagram, this is the hybrid pi model, exact electrical equivalent circuit of BJT. And this one, FET, exact electrical equivalent circuit, high frequency model of field effect transistor. So, same thing is represented here, electrical equivalent circuit of BJT and FET. And see, irrespective of configuration of BJT, that is common emitter, common base or common collector, there always exist only two junctions. Base emitter is one junction, base collector is another junction. So to operate it as an amplifier, it should be operated in the portion of active region. Means base emitter junction is forward bias, base collector junction is reverse bias. So forward biased capacitance is represented here as a CB-E. Reverse bias capacitance is represented as a CB-C. And other terminals, base spreading resistance, RB-E, RB-C, RCE, and the dependent current source. This is electrical equivalent circuit of BJT. Similarly, in the case of FET, for every two terminals, there is a capacitor, G2S one capacitor, G2D one capacitor, D2S one capacitor, internal drain resistance, and dependent current source, GM/VGS. So these are all typical values of all model parameters of hybrid pi related to BJT. GM is the transconductance, 50 milliampere per volt. RBB dash is base spreading resistance, 100 ohms. RB dash E is the resistance between base dash and emitter is 1 kilo ohm. RCE, collector to emitter, 0.1 mega ohms. CB-E is 100 picofarad, CB-C is 1 picofarad, and all these values can be seen from this. And FT is unity gain bandwidth product 100 megahertz. F beta is the beta cutoff frequency 1 megahertz. The typical values, the values may vary. Similarly, for FET, all the capacitance values. Mu is another important parameter generally called as current amplification factor. Mu is equal to Gm into small r suffix small d. So mu is equal to Gm into Rd. And H parameter is generally used for BJT. So similarly, FET Y model parameters will be used. So because there exists a resistor in parallel with a capacitor as a feedback element for this common emitter configuration. By using Miller's theorem, the resistor parallel with the capacitor is moved towards input side and output side using the formulae discussed in the second session, Miller's theorem formulae. So see here, the feedback capacitance is here represented as CB-C into 1 minus K. Feedback resistor is RB-C by 1 minus K. K is the gain VCE by VB-E, which is minus GM-RL. And similarly towards output side, capacitance RB-C into K by K minus 1. CB-C into K minus 1 by K. Because K is a very high value and K is approximately equal to K minus 1. So K and K minus 1 gets cancelled. This value is RB-C. Similarly, CB-C. And in output side, RC is very high value, RB-C is a very high value, RL is small value. Generally in the ranging from 1 kilo ohm to 10 kilo ohm. So two unequal impedances, one is having very high value, one is having very small value. The parallel combination always leads to the smaller value. So represented here RL. Similarly, at the input side, RB dash E parallel with RB dash C by 1 minus K is also equivalent to RB dash E. And this parallel capacitance added. So CB dash E plus CB dash C into 1 minus K. K value here is minus GMRL. So we are substituting here 1 plus GMRL. So C is equal to CB dash E plus CB dash C into 1 plus GMRL. So we'll further using these constraints will simplify the circuit. So that circuit is a simplified circuit. RB dash E and C output side only capacitor, all other resistors are eliminated. This simplified circuit will be used in the next sessions. While analyzing the frequency response of RC coupled amplifier, we'll use this analysis circuit for frequency response analysis. Similarly, applying a Miller's theorem to FET electrical equivalent circuit. So the capacitance is there, moved to back input and output side. So similar analysis, CGD into 1 minus K, CGD into K minus 1 by K. K is a very high value, K minus 1 and K are approximately equal, leads to CGD, and K is VDS by VGS. The answer is minus GM into RL. So parallel combination of capacitors will be added. C1 is equal to CGS plus CGD into 1 plus GM RL. And here also parallel combination representing it as a C2, CGD plus CDS. So this simplified shown in the next slide. So this is the simplified circuit. Only one capacitor at the input side, output side, with a dependent current source and drain resistance. This circuit is again used in analysis of FET RC coupled amplifier or the frequency response analysis of FET circuits. So this is the first circuit we will discuss in the next lecture. Single stage BJT RC coupled amplifier frequency response analysis. This is a cell bias circuit. Voltage source given with the source resistance. CC is called coupling capacitor. It will be there at the input side and output side. Mostly you'll use the same values. That's why the nomenclature given here CC. And one more capacitor is there. CE is the emitter bypass capacitor. So we'll discuss again in the next session. The capacitor in series with this resistor will form the external capacitors in series with the resistor forms a high pass filter, and internal diagram and internal capacitors and how it's related to the frequency response analysis we'll see in the next session. So that's all for this session. We'll see the frequency response analysis in the next session. Thank you.